Deep inside a process plant, a high-pressure centrifugal pump running at full load begins to vibrate. Within seconds, the vibration escalates, a mechanical seal ruptures, and the equipment suddenly halts under a cloud of pressurized steam. The immediate consequence is halted production. Every minute this pump sits idle costs the operation thousands of dollars. A maintenance technician is dispatched, identifies a seized bearing, rapidly replaces it under intense pressure, and gets the line running again. Back at a terminal, the technician closes out the computerized maintenance work order. In the notes section, they type a brief, free text entry, repaired motor, or perhaps fixed pump. The immediate crisis is resolved. The machinery is humming, and operations resume. However, the organization has retained a hidden systemic liability. By logging the event with vague, unstructured text, the maintenance department has created a mystery failure. The record proves that an event occurred and labor was expended, but the physical reality of why the bearing seized in the first place is entirely absent from the historical record. When the next failure inevitably occurs on the same equipment, the team has no formal history to consult. Diagnosing the issue relies entirely on whether the specific technician who performed the last repair happens to be on shift, and whether they remember the specific state of that pump months later. Combing through years of these inconsistent free-form notes to identify chronic problems requires hundreds of hours of manual labor. Engineers are forced to guess at patterns, basing their capital replacement strategies on intuition rather than physical evidence. This is the definition of reactive maintenance. A facility operating this way treats every breakdown as an isolated emergency to be fixed, rather than a mechanical failure to be studied.
To break this cycle, organizations must engineer their maintenance data. They must implement a standardized, structured failure catalog. A failure catalog establishes a controlled vocabulary for maintenance reporting. It is the required mechanism to convert thousands of isolated anecdotal repairs into an expanded, highly queryable database of mechanical truth. The foundation of a functional failure catalog is a structure known as the Problem Cause Action, or PCA, framework. Rather than typing a paragraph, a technician must select codes that answer 3 distinct questions for every event. What was the observable symptom? What was the underlying cause? And what specific remedy was applied? While PCA provides the basic logic, true analytical capability requires a higher degree of granularity. To achieve this, the model must be expanded to align with ISO 14224, the global standard for reliability data, breaking the failure down into 5 distinct elements. This animated diagram illustrates the first of these ISO elements, the symptom. This is the functional failure observed at the asset level, in this case, excessive vibration. The standardized code, VIB-XS, slots into our data matrix to trigger the initial maintenance response. The second element is the component. Here, the system identifies the drive end bearing, populating the matrix with mote-BRG. By precisely isolating the failed subassembly, we geographically narrow the focus of all subsequent diagnostic efforts. Looking at the internal cross-section extracts the third element, the damage mechanism. This documents the exact physical or chemical deterioration, in this instance, severe physical wear, coded as BRG-worn. Zooming out to the surrounding mechanical environment reveals the fourth element, the failure cause. We can see a severe misalignment at the pump and motor coupling. This environmental stressor generated the wear, resulting in the code align-error. This specific tag is the single most critical data point in the entire matrix. Identifying the underlying cause is the only way to dictate an engineering solution that prevents recurrence. Finally, the action completes the record. The technician replaces the bearing and realigns the base, coded as BRG, replace, and realign. By mandating these 5 fields, a routine CMMS work order yields a multidimensional, heavily structured data point that can be filtered, aggregated, and queried alongside thousands of others. Structuring the record enforces a strict separation between how a specific part failed physically and why the failure was allowed to happen systemically. This separation provides the visibility needed to isolate and address systemic failure patterns. To see how this data operates at scale, consider critical asset pump P100. Over 18 months, this pump suffered multiple chronic breakdowns. This timeline tracks the asset's history. At month 0, the pump suffered a bearing failure. Because the technicians utilized the failure catalog, the data tag explicitly captures the root cause: improper lubrication due to degraded oil.
At month 6, the pump fails again. The same bearing is destroyed, but the coded data tells a different story. The ISO tags trace this failure to a slight base plate misalignment, putting excessive load on the shaft. At month 14, the bearing seizes completely. The coded data shows lubrication and alignment were perfect, isolating the cause to a defective manufacturing batch from a supplier. If this facility relied on free text work orders, the maintenance log would simply read, "bearing replaced 3 times." The varying environmental and systemic causes driving those replacements would remain entirely hidden in the text. By utilizing a standardized taxonomy, the reliability team can bypass manual review and algorithmically map the asset. Here, this Pareto chart automatically sorts the timeline data, precisely breaking down the varying root causes attacking P100. The visual evidence dictates an immediate business response. The reliability team implements a precision laser alignment protocol for all pump overhauls and installs online temperature sensors to catch lubrication degradation before it destroys the bearing. Structured data ensures the maintenance department does not simply stockpile spare bearings to prepare for the next outage. It forces them to address the physical reality of the machine. Gathering this caliber of intelligence requires absolute uniformity. A failure catalog only works if the code library is comprehensively standardized across the entire enterprise. You cannot have one facility classifying an event as seal failure while another codes it as leak gasket. To enforce this standard, organizations must establish a cross-functional governance team to oversee the exact definitions of every code in the CMMS. When building the initial library, this governance team relies on a tool called Failure Mode and Effects Analysis, or FMEA. By systematically evaluating how a component can physically degrade, engineers can map out the precise codes needed for the catalog. FMEA allows the organization to seed the library with failure modes that haven't even happened yet, guaranteeing the system is proactive rather than strictly historical. As the library operates, the governance team must guard against the proliferation of other or miscellaneous codes. When technicians are under pressure, catch-all codes become convenient dumping grounds. Using an undefined code completely bypasses the PCA framework, immediately degrading the integrity of the data pool. To prevent this, supervisors must conduct periodic data quality audits, sampling closed work orders to verify that specific, accurate codes are being applied to every repair. A failure catalog is a living operational document. Without strict, ongoing governance, the library will decay into an unwieldy, chaotic list of overlapping definitions, rendering the data completely useless for macro analysis. Once the data architecture is secure, the focus shifts from diagnosing single assets to monitoring the reliability of the entire plant. This diagram maps the continuous improvement loop. Structured data feeds into analysis, where dashboards reveal which failure modes command the most labor hours. This triggers root cause action, using hard data to justify capital upgrades. Results then track back into the data stream. To verify this loop is actually working, management tracks specific key performance indicators tied directly to the failure catalog. This line chart demonstrates a measurable reduction in recurring failures. By targeting the exact causes of bad actor equipment, repeat breakdowns drop over time. Conversely, a secondary chart plots the resulting increase in mean time between failures. Critical asset classes operate for continuously longer intervals. The final metric is the Data Quality Index, which tracks the percentage of work orders closed out with complete and accurate failure codes, proving the organizational culture is maintaining its discipline. The financial result of this discipline is a structural shift in budget allocation. Maintenance spending transitions heavily away from premium cost emergency interventions and into highly predictable, scheduled planned work. Furthermore, the structured database acts as a permanent organizational memory. The nuanced knowledge of how a specific pump fails is no longer tied to a senior technician's memory. It survives employee turnover and remains permanently accessible to the newest hire. By aligning this data structure with global frameworks like ISO 14224, the operation ensures its history remains compatible with evolving asset management systems and enable seamless benchmarking against international industry standards. Engineering maintenance data provides the evidentiary baseline required to move an industrial operation from repeatedly fixing symptoms to systematically identifying the roots of mechanical failure.